in terms of where you all are right now. But once you have a power plant, you obviously want to make that many power plants. On the grid right now, you've got plenty of technologies, wind, solar, natural gas, that have existing supply chains. They have a very robust market. Have you thought through at all, how you build up your supply chains to be cost competitive with those industries?
Yeah, so independent of pick your favorite fusion architecture, they all kind of have similar things going on. So the things that are really, really helpful here are, one, it's like a really concentrated power plant, right? It's power dense. You show up at a single place on a piece of ground and you put a machine there. And that machine's got stuff in it. It's kind of complicated, but it's actually not that much stuff. And you look at how much steel or how much copper or things that are in that machine compared to how much power that machine could make. And it is way different than solar and wind, right? So you have a capital efficiency built in from the power density. Yes, it's more complicated, but you don't actually need to build millions of them. If you think about solar panels, the supply chain for solar panels is you got to basically build billions of cells. If you do offshore wind, you got to build hundreds of millions of wind turbines. There's really only a few places on Earth that you can actually build that stuff at that rate. And they're not in the United States. It's really hard to do that in the United States. But if you actually look at how power is generated today, and you just say, give me all the power plants in the world that are electricity power plants more than 400 megawatts, that's 3,700 plants. 3,700, that's not that many. And they are right now, that's 85% of all the energy, electrical energy generated from those plants. That's $1.5 trillion a year, 5 million people, 3,700 sites. And they're 71% fossil. So they have to be replaced. What are you going to replace them with? It's actually harder to replace them with giant wind turbines that aren't there, they're somewhere else, than it is to show up and put a new type of machine on that site to make that power. That looks like a boiler, that has a steam turbine on it. It was like the steam turbine that was there before. From the grid, it looks like that was there before. So we think there's this inherent advantage, the power density and the fact that you can repower, and that a lot of this stuff looks like sort of a derivative of something that already exists at scale. That can make it so that you have a scalability argument in fusion that is unique to fusion. That was the regulatory. So you make the same argument for Rubik, but the regulatory piece is significantly different. So that gives us some hope. The other piece is, we're talking about building a fusion industry, but really we're talking about building a combinatorial industry. It's not really we're gonna have to do every single thing ourselves in fusion, right? And it's not that you go and you say, give me the people that build thermal coal plants, and I'm gonna teach them to do every single piece of fusion. It's actually give me some people from aerospace, give me some people from traditional power, give me some people from automotive manufacturing, and putting that together, and those things all have scale. When we go to our supply chain, we say, hey, we want to go to 10,000 power plants. Every one of the parts in that plant, you can look and say, hey, here's the reason to believe that you could ever do that, and it's because those industries that we're pulling from already do that. There's 10,000 Walmarts. There's 10,000 737s. Not going very well, but there's 10,000. And so there's a reason to believe that because of the combinatorial